This is the video for Unit 7, Lesson 3 that is about graphs of polynomial and rational functions. Notice that there is not a warm-up for this lesson. I have a warm-up for the lesson, but I'm not going to include it in the video and really don't expect you to do it. It's just some synthetic division problems, and that would have been beneficial to do in class if I had you sitting in front of me, but if you've been keeping up with these videos, you have done plenty of practice on synthetic division, and if you want more practice, make sure that you've done the homework assignment that's attached to the lesson 2 notes. And if you still want more practice with synthetic division, which I just would recommend against, I can send you more or I can give you the warm-up. But if you really want more practice of something, I think that the better thing to spend your time on would be simplifying rational expressions from lesson 1 in the practice day that came after lesson 1. So anyway, make sure that you also have your computer set up that you can be both looking at Desmos and watching this video. I don't know if you want to maybe look at the video on your phone and Desmos on your computer, or if you want to double screen the video and Desmos, or somehow get your setup set up so that you've got both Desmos and the video going at the same time, because I'm going to be walking you through how to do a lot of these problems using Desmos, because this lesson is about graphing. And anyway, I would really rather be in the mountains right now, because, you know, last lesson I wanted to be at the beach. So that's a picture of me in the mountains in my dreams. So as in the previous notes packet, this first page of the notes is more of just something that we were going to talk through in class. And so if you could just kind of track along with me, I want to talk a little bit about, so to interrupt myself, the first part of the lesson is going to be just about graphing polynomial functions, and the second part of the lesson is just going to be about graphing rational functions. And it's not quite half and half. I think that the graphing polynomials will be a little bit more straightforward, and the graphing rationals will be a little bit more involved, and they're a little bit trickier because they've got some things that can be surprising about them. So anyway, let's back up. I'm not going to have you be super fastidious and detail-oriented about graphing the polynomial functions, because we're just trying to draw sketches, general sketches of them. And so the things that I want you to be able to find algebraically and place on a graph are the zeros, the end behavior, and the y-intercept. So starting with zeros, please remember that if the polynomial is a certain degree, so let's say that you've got a 4th degree polynomial, and remember that your degree is the highest exponent in the equation. So you rearrange the equation in standard form. That means that your first term is the x with the highest exponent on it, and you want to make sure that that is the degree of the polynomial, and that degree will tell you how many zeros or how many solutions there are altogether. But remember that sometimes the solutions can be imaginary, and so when you're doing this, you can't have more real solutions than n, which is the degree, but you can have fewer depending on whether there's imaginary solutions, and sometimes double and triple roots then will decrease the number of actual real solutions or real zeros. The other thing that you want to look at is what the function does, and I say here, I call it behavior, so you want to look at the behavior of the function on either side. I just scribbled all over, you can't see this. You want to look at the behavior of the function on either side of the x-intercept, meaning that if, let's say that here's the x-axis, there's a number of different things that could happen. You could have a function that goes through the x-axis, and it's below the x-axis on one side and above the x-axis on the other. And if you remember when we talked in Unit 6 about the intermediate value theorem, we're talking about the value of the function being positive on one side and negative on the other side of the zero, and that proves that there's a zero there. But the other thing that could happen is that you might have a bounce. So a bounce would look like this, and that's when you have a double zero, or it could look like this. So those are double zeros. And the other thing that could happen, and I didn't give myself enough space here, is that if your function on one side acts like it's going to bounce, and then on the other side, instead of bouncing, continues on through, so one side of the zero is positive and one side of the zero, the function's negative. If you were to cover up half of that picture there, on one side of the picture it looks like it's going to bounce down, and on the other side of the picture it looks like it's going to bounce up. That's the general shape for a triple root, and so you kind of also want to be on the lookout for that, and those are some behaviors that I would expect you to be able to sketch when you're drawing the graph. And remember that you will have Desmos, so you're going to graph these in Desmos and then sketch them on your paper. And so just kind of take a look, and you might want to zoom in, for example, on Desmos. I'm also going to include in this video video clips of me talking through graphing these things in Desmos. So just kind of keep in mind that you'll have Desmos in front of you while you're drawing these graphs. The second thing that you want to look at after you consider the zeros of the function is the end behavior. You're going to need to know this by heart here. If the leading coefficient is positive, the right end goes up. If the leading coefficient is negative, the right end goes down. So the leading coefficient, the number that's multiplied in the first term of the function equation, if it's a positive number, then the right side of the graph goes up. And if it's a negative number, the right side of the graph goes down. And then once you've decided if the right end is going up or down, then you want to look at an even degree function. Both ends are doing the same thing. And an odd degree function, I am running out of colors, an odd degree function, the ends are doing opposite things. So decide what the right end is doing, up or down, and then the left end will either do the same or the opposite depending on the degree. And we'll talk through some examples of this, so I'm going to move on. The last thing that you want to look at is the y-intercept. Now this is algebraically how to find the y-intercept. We talked about that also in unit 6. But remember that all of this here just means whatever's that last term, the constant term, what we call the term without an x, is always going to be equal to your y-intercept. So the constant term, positive or negative, you need to keep track of the sign, but that'll be your y-intercept. So just keep in mind that when you're doing that with the y-intercept, that if every single term has an x in it, so that if your last term is like 5x instead of just -3 or something, that there's an x there, that your y-intercept will be 0. If every single term in your polynomial has an x in it, your y-intercept is going to be 0. So those are the 3 things that you have to keep track of when you're graphing: x-intercepts, end behavior, y-intercept. And here at the bottom of the page, I have a picture for you that kind of talks you through all of those things. If you are wanting to be a little bit more picky, although I'm not going to require this, you can look at your mins and maxes and turning points. And we've talked about global is the same as absolute minimum and maximum, local or relative minimum and maximum. And it gives you pictures of your single root, your double root, and your triple root, and what those shapes look like. And this picture also gives you an idea of the end behaviors, that in this particular graph, both ends are going down. And so, and it says at large x, and I like that wording here because that just means as x goes to infinity. So as x goes to positive infinity, you're saying that you've got numbers that are getting really negative really fast. And so that graph is just going to keep going down forever. So take a minute if you want, pause the video and just take a look at this example and make sure that all those things that it says here make sense to you and that they kind of correlate with what you've already learned about polynomial functions. So on this page, we're going to draw together 6 graphs of polynomial functions. And rather than using Desmos video segments here, because I think that you can do the Desmos part without me walking you through it step by step, make sure that you have Desmos open. And I'm going to include a screenshot of my Desmos graph and how it looks on my screen. I'm going to kind of put a picture inside of a picture for that. And then I'm going to talk about the graph on Desmos and how you can use that to help you draw the graph on the paper. What you'll see here is that I didn't give you any grids. I just gave you the x-axis with hash marks and a y-axis without hash marks because sometimes the y-intercept is going to be kind of a big number. And so really I want you to focus on the x-intercepts or the zeros and the end behavior on both the left and the right, the up and down aspect of the end behavior, and look for any places where there might be a change of direction that doesn't trigger an x-intercept, which you'll see what I'm talking about in number 3 and number 5. Look for double or triple roots and make sure that you draw those, and I'll zoom in on some of them when I'm showing you the Desmos aspect of the graph. And so let me just start here with number 1. And the first thing that you want to do for each of these is factor the expression. And I'm going to ask that you factor them on your own. And then pause the video, factor the expression, and then come back to the video and double check that you have factored it correctly. And just a hint before you pause the video for number 1 that you need to factor a GCF of x first before you factor then the remaining quadratic trinomial, probably using either box method or grouping or whatever method it is that you use. Remember, be careful of slide and divide because it's tricky. So go ahead and factor that. And you should have gotten f of x equals x times 3x minus 2 times x plus 3. And so the first thing that you want to do is decide what your x-intercepts or your zeros are. And so your zeros are x equals 0. That's the first one. X equals positive 2/3. That's the second one. And x equals negative 3. That's the third one. Make sure that you see where I got each of those from. I'll kind of color code them in this one so that you can track with my thinking there. And then the next thing that you want to do is decide about the end behavior. And so for the end behavior, what you want to look at is the first term. So notice that this polynomial is already written in standard form. The exponents are written in decreasing order, so 3, 2, 1. It's a third degree polynomial because the biggest exponent is 3. And this first term, your degree is odd, and your leading coefficient is positive. So the leading coefficient positive tells you that the right end goes up, and your odd degree tells you that the ends are going in opposite directions. And so your end behavior is going to look something like this. These are your zeros or your x-intercepts. And then we said just a little while ago that your y-intercept is going to be whatever the constant term is, but it doesn't say anything down here. So that would be like saying x or minus 6x plus 0 there. And so your y-intercept is going to be 0. Remember that anytime you have an x-intercept that's 0, that will automatically also be your y-intercept. Now you want to go ahead and draw this graph in Desmos. And so I am going to, without any fairy dust music, make that graph appear. There it is. It's kind of in my space. Wonder if I can make that move. Hang on a second. Let me see if I can move that over here. Ooh. There we go. That's going to be a little bit better for you to look at. I'm just going to zoom in on it over here. Okay. Sorry, I should have taken care of all of that before I open the video back up again. Anyway, so you should type in the equation into Desmos, and then you don't need to resize it. I resized it so that I wasn't screenshotting the entire screen on my iPad, but I just wanted to kind of move the graph over closer to the equation and give you part of the screen. So anyway, the other thing that I did to help me graph this is I clicked on what the computer would consider the special points. So in Desmos will give you specific points at the x-intercepts, y-intercepts, at maxes and mins, so places where the graph changes direction, as well as if you've got two equations graphed on the same graph space, it'll tell you or show you where two graphs intersect. And we did a little bit of that in the other lesson. Looked at solving rational function equations by graphing both sides of the equation and then looking where the intersection happens. So here I clicked on all of the x-intercepts, y-intercepts, and maxes and mins so that I can kind of get an idea of where I'm going to put points on this graph. And I'll start by double checking the x-intercepts or the zeros that I had said were x-intercepts or solutions, and there are these three: the -3, the 0, and then 0.67 is your 2/3, your positive 2/3. And so I'm going to go ahead and graph those 3 points: -3, 0, and then this positive 2/3 is going to be somewhere right in there. And so here, the y-intercept is the same as the x equals 0. And then the next thing that I want to do is think about the fact that my end behavior has the right end going up and the left end going down. And I think I'm going to elongate that in a minute. Now, if I look at the maximum here on this end, there's my clock, and I'm just going to talk right through the clock going off. The y value of that maximum is 16, and that's awfully hard to draw, so I'm not going to draw that up at 16. I'm not going to give you a realistic idea of the size of that graph, but I'm just going to kind of make that go up and come back down. But then the minimum over here, that minimum is just -1 on the y-axis. So that doesn't dip very far below the axis there very much at all. And then, like I said, I think that I'm going to extend the ends on the left and the right now that I'm zoomed out a little bit. and just draw that like this, and draw this one. I actually don't like that little bumpy bump there, so I'm going to draw this one going down. And really, I don't need much more than that. I just need to be able to see that your x-intercepts are what your x-intercepts are, your y-intercept is what your y-intercept is, and I need to see the end behavior of your graph. And the funny thing about the clock going off right then was because a friend was texting me, which shows up on my iPad. You can't see it, but I can. The clock went off, and I'm fussing about the clock, and then I get this text message from a friend who's trying to FaceTime me, and so I got distracted. Anyway, I got rid of all of the other stuff that I was just talking about, the text messages and the FaceTimes, and all of that took about an hour, so my clock is going to go off, and I'm not going to stop talking again. So anyway, let's go on and look at number 2. So this is merely a quadratic, but before you go to town factoring this, ask yourself, what do you notice? You should notice that there's a GCF, and that is a GCF of 2. So factor out the 2 first, and then factoring what's left shouldn't be difficult, and it won't have a leading coefficient. Remember to always check for a GCF first. It has to be the first thing you do. So pause it real quick, factor this. And you should have gotten f of x equals 2, there's the 2, and you still have to keep the 2 written in the front, times x plus 1 times x minus 3. Your x-intercepts are -1 and +3. Remember that the 2 doesn't have a variable attached to it, so it can't be equal to 0. But the x plus 1 gives us an x-intercept of -1, and the x minus 3 gives us the x-intercept of 3. The leading term, or the front term, the first term of the polynomial, the degree is even, which means that the ends are going in the same direction. And the leading coefficient is positive, and so your end behavior is both ends are going up. The positive tells you that the right end is going up, and even means that they're both doing the same thing. And so you're going to, and your y-intercept then is going to be -6. So y equals -6, your y-intercept. So the next thing that we're going to do is look at the graph of this. So why don't you go ahead and pause this, graph it on Desmos, and in a moment the Desmos graph that I've drawn is going to appear on your screen magically. So your graph should look something like this. And remember that the x-intercepts here and here are that -1 and 3. Remember that you can click on the important points and it will show those to you. And then the y-intercept here at -6, we've already said, and the end behaviors, both ends going up, we already said. You can keep in mind this turning point, or the minimum at 1, -8 when you graph this function. So start with your x-intercepts at -1 and +3, and your end behavior goes up, so you kind of want to be thinking in that direction. Your y-intercept down here at -6, and you know that there was a minimum at 1, -8, and those aren't going to be super accurate. And so then you're going to kind of draw this shape. And then I'm going to tidy up my ends here. So I'm going to erase a little bit and redraw stuff because, you know, I'm like that. Doesn't surprise any of you at this point. And draw that like this. Oh, that was probably the least steady line I've ever drawn. There we go. So there's your number 2. Now in number 3, again, I'll ask you, what do you notice to factor this? You should notice that there's a GCF of 2, but I would recommend actually using the GCF of -2, because that way if you factor out the -2, you have a positive leading coefficient. So start by doing -2 times x to the 4th, then it'll be minus 3x to the 2nd minus 4. And when you're thinking about this, to factor it, think, how would I factor x squared minus 3x minus 4, which is x minus 4 times x plus 1. But then you have to make those squared. So I guess I'm going to walk this whole thing through with you. So you're going to end up with f of x equals, and then it's the -2 here, so -2, and then make each of these squared. So x squared minus 4 times x squared plus 1. But this can be factored farther. And so your final factored form here is going to be, let me zoom in on this for a second for you to write stuff. Your final factored form here then is going to be f of x equals, and you have to keep that -2 when you write it. X squared plus 1 cannot be factored any farther. And then x squared minus 4 becomes x plus 2, x minus 2. So your x-intercepts are +2 and -2. And then from this, you have imaginary roots. And so you could also, if you wanted to, put plus and minus 1i. If you do x squared plus 1 equals 0 and solve that, x squared equals -1. That's from this. But because we're talking about graphing here, we can't graph positive and negative I. You can't graph I because it's imaginary. And so I'm going to, my x-intercepts are positive and -2. Coming back to my original equation, remember that you look at the leading term here to decide about the end behavior, and it's even degree. So even degree means that the ends do the same thing. And your leading coefficient is negative, so your right end goes down. So in this graph, both ends are going to be going down. That's your end behavior. And then last but not least, the y-intercept is 8. So your y-intercept is y equals 8. So I'm going to graph the x-intercepts, the positive and -2. And so I've got a point here, and I've got a point here. And that y equals 8, it clearly, if I keep the same scale on the y-axis that I have on the x-axis, I don't have room for it. Oh, and I forgot to give you the Desmos graph. So let's take a look at the Desmos graph. Go ahead and pause this and type this into Desmos. So this is what your graph should look like in Desmos, and I clicked on the x intercepts here and here, that's the positive and negative 2. Your y-intercept, that's 8. Notice that your end behavior is down on both ends. And I tried to do this a couple different ways and couldn't. I have a local maximum here and here, and the y value should be the same, this 12.5, but I couldn't, if I actually clicked on this point, the value of the point covered up the other maximum. So just imagine that I've got all of those points clicked on. Anyway, that kind of gives you a feel for how this is graphed, but really when you graph this, and I'm going to go back and erase some of the things that I scribbled. When you graph this, what you want to highlight is just this idea of having the up down stuff that doesn't have any x-intercepts in there. So you have changes of direction that aren't associated with x-intercepts, and that's when you end up with imaginary solutions, and that's where our positive and negative 1i come from. But remember that you can't graph, or you can't predict what the graph is going to look like based on what the I is. Just know that there are imaginary solutions to this equation or to this graph because of everything that's going on right there. You can tell by looking at the graph that there's going to be some imaginary solutions. So let's go ahead and graph this. I already graphed the two x-intercepts, and if the y-intercept is somewhere, let's just randomly say here, it's going to be somewhere positive, then I've got my end behavior that goes down in both of these places. And so here I'm going to go like that. And this one, that's bad. I need to do a better job of making that kind of look like the other side. But anyway, you get the idea there. That's a general sketch of the graph for number 3. So for number 4, if a polynomial that I need you to graph is not factorable, what I'll do then is to tell you to divide by a certain x value, meaning use synthetic division, and then whatever's left should be factorable. Now, the other thing that you want to notice here is, again, I've given you a GCF, or an equation that has a numeric GCF, so really factor out that negative 2 so that you've got x cubed minus 5x squared plus 3x, and then plus 9. And then use only what's inside the parentheses for your synthetic division. And so over on the side here, then I'm going to write and it says there to divide by x equals 3. So bring down the 1, and that's negative 2. Negative 2 times 3 is negative 6. Negative 3 times positive 3 is negative 9. That's what we want it to do. I'm telling you to divide by that because it is a factor. And so now I've got x squared minus 2x minus 3. And that itself factors to x minus 3 times x plus 1. But now look and see what I did here. I told you to divide by x equals 3, and remember that what that means is that x minus 3 is a factor. And after I divided by x equals 3, x minus 3 was a factor. So actually x minus 3 is going to be a factor twice. So my factored form is going to be f of x equals, don't forget your negative 2, x minus 3 twice, so with the exponent of 2, times x plus 1. And this sucker right here, that's going to give us that double root look with the bounce on the graph, where the function is on the same side of the x-axis on both left and the right of it. So let's start with a picture of the graph. Go ahead and put this into Desmos. Pause the video for a second and type it into Desmos, and in the meantime I will bring up a graph screenshot for myself. Okay, so one of the I love the software I use to record these videos, but I can't make these graphs straight. Anytime I pull in an image that I've screenshotted or am copying from somewhere else onto the video, it can't go straight. I need to do all of this in iMovie. Anyway, you don't care about any of that. So in your factored form of the equation, you had -2 times x plus 1 times x minus 3 squared. So you've got the x equals -1, and that's a single root, and you can tell because it's positive on the left and negative on the right. The function itself is above the x-axis on the left, that makes it positive, and it's below the x-axis on the right, that makes it negative. But here, this is where you've got your x minus 3 is a double root. X minus 3 in parentheses to the second power means that positive 3 is a root twice, and so it's going to act like that bounce. So like you threw a basketball against the ceiling and it came back down again, and that is the behavior of the graph around a double root, and we talked about that on the first page for a minute. So anyway, when you draw the graph, we didn't talk about the end behavior or any of that stuff. I should have done that first. So your end behavior here, look at the first term. It's odd degree, and so odd degree says that the ends are going to be different. They go in different directions. And your leading coefficient is negative, so your right end is down. So you're going to have an end behavior that looks like this: right end down, left end up. And the ends are different. So the other thing that I want you to identify is that the x-intercepts are +3, +3, and -1, and the y-intercept over here is -18, which is difficult to draw accurately. But let's start with here. We know we have a root at -1. We know we have a double root at +3, and the behavior here is that the graph goes down on either side of it. And in the graph we saw that there was a minimum just to the right of the y-intercept. So if my y-intercept is, we're just going to make it there, and we'll make that minimum right about there. So then the graph can go like this. The right end goes down because the leading coefficient is -2, and then the rest of the graph kind of goes up like this, and then the rest of the graph on the left goes up. And so that's what your graph is going to look like. So number 5, there is no GCF here, so you can't take out a GCF to start with. Then I give you this hint that you are going to divide by x equals 2. You're going to do synthetic division for that. But your answer is going to be a quadratic that is not factorable. And that means that you're going to have some imaginary roots. And we'll talk about what that looks like in a minute, but let's start with the synthetic division. And I'm going to do that way down at the bottom of the screen here. So the synthetic division is going to look like this. 3, negative 10, positive 10, and negative 4. And I'm dividing by 2, bring down the 3, negative 4, negative 8, positive 2, positive 4. And remember that if I'm telling you divide by this in order to draw a graph, what I'm telling you to divide by is a factor. And so that x minus 2 is a factor, and therefore you should get 0 when you divide by it. So the resulting quadratic, this 3x squared minus 4x plus 2, I've already told you is not factorable. If you were to do the quadratic formula with this, which you don't need to because you're graphing it, I didn't ask you to solve it, you would get imaginary answers. So coming back up here, then factored form, f of x equals what you divided by, x minus 2, and then your quadratic form, 3x squared minus 4x plus 2. And that means that your only x-intercept is positive 2, and I'm not going to ask you to find the negative solutions for the quadratic because I'm asking you to graph this. The end behavior, here we have odd degree, so the ends are going to be different, and a positive leading coefficient. And so the right end is going to go up and the left end is going to go down. So your end behavior is going to look like that. And so your y-intercept is going to be the negative 4. So y equals negative 4. And what I would like for you to do is take a minute and type this equation into Desmos and get a good look at that. And I'm going to pause the video for a minute while I pull up my Desmos screenshot. All right, so your graph here looks like this, or it should look like this. Again, I clicked on my only x-intercept, my y-intercept, which we already decided. And then this whole mess right in here, because you've got changes of direction that are not associated with an x-intercept, there's going to be imaginary solutions to this polynomial. And that's the kind of shape that happens. If that was going up through the x-axis and back down through the x-axis and up through the x-axis again, then you would have more x-intercepts and you would have more real solutions. But when you see this kind of shape happening and it's not going through the x-axis, then you know that you have imaginary solutions. They're not real solutions. So I'm going to come back up here and I am going to, I feel like the whole thing isn't straight. Hang on a second. Let me see if I can make that straight. I'm going to mess it up. There we go. So I'm going to graph my one x-intercept, which is x is equal to positive 2, and then my y-intercept, which is negative 4, and then I've got this little doojiggy here that goes up to that point and down to that point, and it's all kind of tight, real tight inside of that space. So let's just kind of zoom in here, and you can't really, your end behavior is down here and up here, and then here you've got that little doojiggy, kind of like that. And I'm actually going to fix this end behavior and just make it a little bit steeper. If you can see up here, that's pretty steep, and so I'm going to draw that fairly steep and much smoother. And there's your graph for number 5. Now, in number 6, there wasn't really a good reason for me to give you something that you needed to factor for this equation. I really just wanted to focus on the fact that here you have a factor that's to the third power, and that gives you a triple root, and so you've got that weird shape of a triple root. So when you type this into Desmos, just use the parentheses and the exponent exactly, type the equation exactly as it is. And by the way, you should have, you should be able to tell me that your x-intercepts are -1, -1, -1. That's the triple root, and +3. And don't worry about the y-intercept and the end behavior. We'll look at that from the graph. So take a minute and pull up Desmos and graph this. And I still feel like it's not straight. That's going to make me nuts. Okay, so take just a minute, graph this, and I'll pull up my screenshot. So this is what my screen looks like when I graph this function. Notice that we do have the x-intercepts at -1 and +3. We've got a y-intercept at -3, and the reason that it looks really close to the origin is because I've compressed my graph. Your graph might not be that compressed, but I wanted to show you this local minimum, and it's also global or absolute minimum at 2, -27. In order to make the -27 piece visible to you in the video, I needed to compress my graph. If you're graphing on any kind of, with Desmos on any kind of handheld device, it's pretty easy. If you can see the x or y axis, use 2 fingers to squeeze or to drag out one of the axes, but you have to put both fingers directly on the axis, and it will change the scale of just that one axis. It's not all that important for this graph. Just know that it goes way down and then comes back up again. Get your x and y intercepts graphed, but I want you to pay special attention. I've actually got another graph where I zoomed in just on the shape of that. And if you kind of like take your hand and cover up the screen, on the left, you can almost imagine that being a bounce, like a double root would be. And if you cover up the other half of the screen on the right, the shape of that looks like it could be another bounce. But the graph itself actually keeps going straight on through, so that you've got this kind of a shape. And that's the shape that your graph should take when you are graphing something that has a triple root. And I still feel like that graph's not straight, and that makes me batty. So anyway, here are your x-intercepts, and you'll see that your y-intercept in Desmos is -3, and you'll see that your end behavior is both ends going up. So your end behavior is both ends going up, and your y-intercept is y equals -3. And so here I'm going to graph my -1. That's where my triple root is going to be. And then I'm going to graph another x-intercept at +3. And then I am going to draw that shape here that kind of looks like this. And so here's my y-intercept at -3, and I don't like that. Sorry, you guys, my personality. I just have to draw it right. So anyway, let's try that again. So that's a little bit better. So y is -3. And then my minimum is way, way, way down there, and you're just not going to be able to draw it to scale. My end behavior, both ends are going up. And the thing that I would really look at on a test is, did you draw this shape in such a way that it really shows me that you understand this kind of a curve. That it doesn't just go straight on through, and that you see the difference in the shape of the curve at -1, that you see the difference here compared to here. And I need to see that difference. Don't just draw a straight line through there. The remainder of this packet is going to be graphing rational functions, and the rational functions that we're looking at are rational functions are a little bit tricky to graph because there's a lot of different, I would say, moving parts. There are a lot of different things about the rational function graphs that are dependent on the algebra of the equation, and so you need to be working very closely both with the equation and the graph that you see on the screen. Now, excuse me, I don't know what that little b is there for. I just saw that b. I'm going to have to go back and fix that. I'm not sure where that came from. You guys totally crack up when you're watching my videos. I know you do, laughing at me. So the graphs of the rational functions, first of all, what you need to know straight up front is that we're not going to be doing graphs that have slant asymptotes. Which means that your teacher in Algebra 2 may have called them oblique asymptotes or slant asymptotes. All of the asymptotes we're dealing with are either going to be horizontal or vertical, y equals a number or x equals a number, and we're not going to do the slanted line asymptotes. Those get a little bit more involved, and we don't really need to address those. So what I want to do here, and let's just, take a look at a couple of these graphs to see what I'm talking about. Notice that, let's just say, for example, this second graph that has a b, a random b. What in the world? Why is there a b there? It's just like a b. I have no idea why that's there. So if we take a look at this graph, what you'll see is, and what I kind of want you, the way I want you to kind of think through this is start with the x values and look at what x values are represented. So if this asymptote happens at x equals -1, and this asymptote happens at x equals +1, those are x values that are missing from the graph, meaning that they're missing from the domain of the graph. You would have all real numbers except -1 and +1, or your domain would be -infinity to -1. In fact, let me highlight that as I'm talking. So -infinity to -1, -1 to +1, and then +1 to +infinity. Those are the x values on this graph that are represented, and they don't include -1 or +1. And so you need to be thinking about that. Now, of course, I am going to ask you about things like what's the x-intercept, what's the y-intercept in this graph. They're the same thing that we've asked before. We can also talk about end behavior, although I'm not going to really talk about end behavior in this unit at this point. I won't add it this year, but if you're watching this video in some year other than 2020, then I may add it. But the end behavior would be whatever the horizontal asymptote is. And here, let's say that the horizontal asymptote in this graph is y equals +1. The ends of the graph get closer and closer to this horizontal asymptote. The difference between a horizontal asymptote and a vertical asymptote is that the graph can cross a horizontal asymptote in the middle. So you might have a situation like this, where in this last graph here, where your horizontal asymptote here is y equals 0, and that's your end behavior as well. But then in the middle, you've got this place where the actual function crosses the horizontal asymptote. That's perfectly valid. What will never happen is that a vertical asymptote will be crossed. A vertical asymptote will never ever be crossed. The other thing that we're going to talk about that you can't see in these pictures are holes, and we'll talk about how to compute a hole and how to know if there's a hole. What I want to do is start with some of the algebra first, and then we'll get into some of the graphs. So let's remind ourselves about domain. In these first few problems, I'm asking you to find the domain. And remember that for domain, you are only looking at the denominators and what makes the denominator equal to 0. So you're literally just going to say, okay, I want x minus 5 to not equal 0. So x does not equal positive 5. And that's not the domain. What we're going to do then is we're going to write the domain in interval notation. And so the domain would be then negative infinity to 5, and then 5 to positive infinity. In this next one, you have to factor a denominator if it can be factored. And so your denominator here is x plus 4 times x minus 4. Now, FYI, you may notice that the numerator can also be factored, and it would be x plus 7 times x minus 4. And because you were paying attention when we did lesson 1, and you know that if anything can be canceled, it should be canceled. And if you remember learning about holes from last year, the x minus 4 can be canceled, and therefore there's a hole at x equals 4. We don't care about any of that if the question is only what is the domain. Because the domain is that x cannot equal positive or negative 4. That's it. That's the only thing you care about for the domain. And it doesn't matter if one of those x values is an asymptote. Hang on a second. So this one is an asymptote. And if you were to graph this, you'd see that. And this one is going to be a hole. It doesn't matter because both of those x values are missing from the domain. So if I ask you what's the domain here, your domain is negative infinity to negative 4. You skip the negative 4 and then go from negative 4 to positive 4. So negative 4 is not included, and then positive 4 is not included, and then you go from 4 to positive infinity. And in letter C, I have already factored the denominator for you, shame on me. And so here, x cannot equal positive 1/2, and x cannot equal negative 3. So the way you would write that, if I ask you for the domain, is negative infinity to negative 3. You always have to do the smaller number. Negative 3 to positive 1/2. And then positive 1/2 to positive infinity. Now, this last one is a little tricky, so let's take a look at this off to the side. X squared plus 9 can't equal 0. That means that x squared cannot equal negative 9, which means that x squared cannot equal plus or minus 3i. But wait, the I tells you that that's an imaginary solution. So there's no real number that would make x squared plus 9 equal to 0. So there's no way that this denominator can be equal to 0. Now, if you want to, you can look at the graph, but If you know that the denominator cannot equal 0, and that's the only thing in this problem that could restrict the domain, then your domain here is going to be all real numbers. And you technically don't need to look at the graph. But given that I know that some of you are going to want to think about this, let me just show you that the graph of that function, numerator 3x plus 5, denominator x squared plus 9, is going to look like this. And really, if there was going to be something of interest happening in this graph, it would be in through here, but there really aren't any missing x values. There's clearly not any asymptotes. And so if you want to go ahead and fiddle with this graph on your own and zoom in and zoom out and click on different things, this is a really good time to do that. But the bottom line is you were asked about the domain of the graph, and the domain of the graph is all real numbers because there are no vertical asymptotes, and there are no holes, and there's no value that would make the denominator equal to 0. Now, I'm also going to ask you to look at the x and y intercepts, just like we would with any function that we're graphing. And the rules for the x-intercepts, let me start with the x-intercepts, are that you want to find where the numerator is equal to 0. So unlike the domain where you set the denominator not equal to 0, for the x-intercepts you set the numerator equal to 0. And then for the y-intercept, you make all of the x's 0, just like you would for any problem where I ask you for a y-intercept. And I'm going to show you a nifty little trick where you just look for a fraction and reduce the fraction. So anyway, that's the x and y-intercepts. Let me start with all the x-intercepts. And remember, for the x-intercepts, you're going to make set all the numerators equal to 0. And so here, to find my x-intercept, I'm going to say 3x plus 2 equals 0. So 3x equals -2 and x equals -2/3. That's your x-intercept for A. And letter B, you're going to need to factor the numerator, so that's going to end up being x minus 8 times x plus 3. And so if you do x minus 8 times x plus 3 equals 0, x equals +8, and x equals -3 would be your x-intercepts. For letter C, that's not factorable. And if you set this equal to 0, you would end up with x equals plus or minus I radical 2. Well, you can't have an imaginary x-intercept. That's really the finite, or the more nuanced difference between, you know how when we talked about x-intercepts and roots and zeros and solutions, that those 4 words mean approximately the same thing, but they don't mean exactly the same thing. The reason that they don't mean exactly the same thing is because an x-intercept has to be a concrete thing. You can point to a place on the x-axis where the graph goes through the x-axis. Here, I'm saying that this graph would have imaginary solutions. If you were to solve this equation, set the equation equal to 0 and solve that equation, you would get these 2 imaginary answers, positive I radical 2 and negative I radical 2, and those are not going to be reflected in your x-intercepts. Now, if you were to actually graph this, what you'll see here in this graph is that you have a horizontal asymptote on the x-axis, and that in the middle, even in the middle, the graph doesn't touch the x-axis, and so there are no x-intercepts. And so if I said to you, what's the x-intercept here, you would say there is no x-intercept. So for letter C, no x-intercepts. And so the answer to that question then is none. Or no real. If it would really bother you, you could say no real x-intercept. Okay. So that's letter C. And then letter D, to find the x-intercept, 2x plus 9 equals 0, 2x equals negative 9, and x equals negative 9 over 2. There's your x-intercept for letter D. So the next thing that you're asked to do is find the y-intercept. And so what I want you to do is look back at the equation and remember that we said that we were going to set all of the x values equal to 0. And so you could, if you really want to, put a 0 here and put a 0 here. 3 times 0 is 0, plus 2 is 2, 0 minus 6, negative 6. But what's going to happen is, if you just look at what the, let me find a better color for this. If you just look at whatever term in the numerator doesn't have an x, and whatever term in the denominator doesn't have an x, and then if you cross out everything else, or if I was teaching this to you in class, I would take my hand and put it over that part of the equation that I just crossed out in black. All you're looking at here is the fraction 2 over negative 6. So your y-intercept here, your y-intercept is going to be y equals negative 2 over 6. But of course, you have to reduce all fractions, and so that's going to be negative 1/3. So same thing here. I want to look specifically at the term without an x in the numerator and the term without an x in the denominator. And then I'm going to not even look at or cover up or actually physically cross out everything else. And so my y-intercept here is going to be negative 24. Y equals, sorry, you can't see what I'm erasing, but negative 24 over positive 12. And then you have to simplify that fraction, so it's going to be y equals negative 2. In this one, now you've already got the graph, so you can kind of see in the graph that your y-intercept is going to be a negative number, and it's going to be a small number because it's fairly close to 0. So let's come back up here. Look for the number in the numerator and the number in the denominator that don't have an x, or the constant terms. Ignore everything else. And so your y-intercept is going to be y equals 2 over negative 4. And that's going to be y equals negative 1/2. Now in this last one, this problem is also a little bit tricky because the numerator has a number or a constant term that doesn't have an x in it, but the denominator doesn't. And if you think about 0, you can't have anything over the 0. So you probably understand that if we're looking at 9 over 0, which is not, it's undefined, it's not something that you can use as a mathematical answer to anything, then there is no y-intercept. But if you're like me, you want to kind of look at the graph. And voila, here's the graph of that function. And you should notice here that you've got a you've got a vertical asymptote on the y-axis, which means that, remember that a vertical asymptote can never be crossed. Even somewhere off the graph screen, this asymptote is not going to be crossed over by the graph, so there will never be a value where y is equal to, or where x is equal to 0, so there's never going to be a place where the graph crosses the y-axis. And so here you can just say that for the y-intercept, because y equals 9 over 0 is undefined, no y-intercept. So on this page, we're going to be talking about holes and asymptotes, both vertical asymptotes and horizontal asymptotes. Notice that I have a heavier line between vertical and horizontal asymptotes, and that's because if you look at what I have over here, this is all based on the x values. And if you look over here, your horizontal asymptotes are related to your y values. So let's talk about the x values. And when you look at numbers that are excluded from the domain, meaning any number that, that would make the denominator equal to 0, each x value that's missing from the domain is either a whole or an asymptote, can't be both. And so if you turn the page back to the problem that we did, example 7, letter B, and I had been talking about the one of the factors was going to cancel, but that doesn't change the domain. It just means that that's a whole and not an asymptote, but it's still an x value that's not in the domain. You can tell that something's a whole based on whether a factor cancels. If nothing cancels, there's no whole. If something cancels, the factor that canceled, that's going to be the x value for the whole. Anything that in the denominator that is a restriction on the domain but does not cancel with something in the numerator, then that's going to be automatically a vertical asymptote. I am also going to ask you to find the y value of the whole, and we'll walk through a couple examples of that in the rest of this packet, but you essentially cancel the factors that can cancel. Make note that that's the value of the x value of the whole, and then substitute that value, that x value, back into the expression after having canceled. Because if you substitute it in before it's canceled, then you're going to make the denominator 0, which you can't have. But if you substitute it in after, what happens then is that you are solving for y with everything that's left. Any denominator value that would make the denominator 0 that doesn't cancel with anything in the numerator, then that is automatically a vertical asymptote. And we're going to walk through examples of all of this multiple times. When you look at the horizontal asymptotes, you have to look at the degree. So the numerator is a polynomial and the denominator is a polynomial. And if the degree of the numerator and denominator are the same, you're going to look at the leading coefficients. If the degree of the denominator is bigger than the degree of the numerator, then your horizontal asymptote is automatically y equals 0. Period. 0 is your answer. And that's because the denominator is going to get bigger a lot faster than the numerator as you go to infinity, and the denominator of any number over infinity or over an infinitely big number is going to be 0. We'll practice some of those. They're fairly straightforward. So let's talk about finding holes and just vertical asymptotes in this one. So take a look at letter A, and you'll see that nothing cancels. If nothing cancels, then there is no hole. And so if I ask you what are the holes, you're going to say there are no holes. And then if you want to look for the vertical asymptotes, you have to set the denominator equal to 0 or say not equal to 0. So here I'm going to say, okay, x plus 2 can't equal 0, and 3x minus 1 can't equal 0. So x cannot equal negative 2, and x cannot equal 1/3. So you have vertical asymptotes. Let me abbreviate that as VA at x equals negative 2 and x equals positive 1/3. So this graph would have two vertical asymptotes, negative 2 and 1/3. And I'm not going to graph these now. If you want to pause the video and graph them out of curiosity, be my guest. Now notice in letter B that your factor of x minus 2 in the bottom cancels with the entire numerator. And so that simplified expression can be rewritten as 1 over x minus 1. What that also means is that x equals 2 is the location of a hole. And then what I had said was that if you want to find the y value of the hole, you cancel the factor that can be canceled first, and then you substitute the x value in to the simplified expression. 2 minus 1 is 1, 1 over 1 is 1. So this is your y value. And so now you're going to tell me that there's a hole at x value 2, y value 1. So if you were to graph this in Desmos, what you would find is that as you drag your finger over the top of the function graph, and you can kind of see the x and y values as they change as you drag over that. Sorry, did I say with your finger? Because I'm thinking about my iPad, but with your computer, if you just take your cursor and you drag over the top of the graph, you can see the x and y values change. And if you carefully hover over x equals 2, it should say that the y value is undefined, meaning that there actually is a missing y value at y equals 1. This is a missing point. This is not part of the graph. It's a missing point. Whatever's not a hole has to be a vertical asymptote. And so here you're going to say that you have a vertical asymptote at x equals positive 1. Now in letter C, I'm going to ask that you pause the video, pause and factor, and both the numerator and denominator can be factored. So pause and factor, pause and factor. And when you paused the video and factored the numerator and the denominator, you should have gotten in the numerator 2x minus 1 times x plus 3. And in the denominator, you got 2x plus 1 times 2x minus 1. And as soon as you see that there's a factor that cancels, then you also want to rewrite your expression here as x plus 3 over 2x plus 1. The pink canceling means that there's a hole where x is equal to positive 1/2. 2x minus 1 equals 0. And so to find the y value of the hole, I'm going to substitute so that's going to be 3.5, which is 7/2, over 2 times 1/2 is 1, 1 plus 1 is 2, and 7/2 times 1/2 is equal to 7/4. Okay, and so my whole, that's the y value of my whole. So the answer to my question here, the x value is the 1/2, the y value is the 7/4, and so the whole is 1/2 comma 7/4. And then remember that whatever's not a whole is a vertical asymptote. So you've got a vertical asymptote there at -1/2. Vertical asymptote at x equals -1/2. So in this bottom section, I want you to find the horizontal asymptotes. And the first thing that you want to look at is the degree of the numerator and the degree of the denominator. You essentially don't even need to think about, and you don't want to cross it out entirely, but you kind of don't need to think about any of that when you're thinking about horizontal asymptotes. Just for the purpose of horizontal asymptotes, you only need to worry about the first term. And in fact, if the degrees are the same, then you think about the leading coefficient and you literally look at that fraction that is the 2/1. And so here your horizontal asymptote is y equals 2/1, which is just 2. So you've got a horizontal asymptote at 2. Here, your degree is 2 in the denominator, but if there's no x at all, then your degree is 0. If the degree of the denominator is bigger than the degree of the numerator, then you have a horizontal asymptote at y equals 0. it's always going to be 0. If the degree of the denominator is bigger than the degree of the numerator, that means that the number, as x goes to infinity, the number in the denominator gets bigger faster than the number in the numerator. And so the value of the whole fraction is going to get infinitely close to 0. Here, the denominator has degree 2, the numerator has degree 1, and so my horizontal asymptote again is y equals 0. And in letter D, you've got degree 2 and in the denominator and degree 2 in the numerator. Both are degree 2. And so in this case, you look at the leading coefficients, and your horizontal asymptote is going to be that fraction. So your horizontal asymptote is y equals 2 over 3. Now, before you continue with the video, I haven't really done much with Desmos for the last couple of pages. Haven't asked you to do much, but the last that's what you heard me moving papers around over here. The last 4 problems, the next 2 pages are going to be 4 graphs, 4 rational function graphs, and you're going to need to have Desmos for that. So pause the video and get your computer set up to both watch the video and to look at Desmos, or be able to switch back and forth, like write down the problems and then go to Desmos and graph it and then come back to the problem. However that works for you, and we'll come back in a few seconds. And we're back. Well, I don't know who we means. I don't know, what was I thinking? But anyway, we're back. So when you are asked to graph a rational function, similarly to the polynomial functions, you want to start by graphing or computing the x and y intercepts, just to make sure that you have an idea of where the graph is going to cross the axes. You need to know what are going to be the holes and vertical asymptotes. Remember, that's related to where the denominator is equal to 0. Let's just kind of make a note about that. So that's where the denominator would equal 0, because then you can't, that would be no x value there on the graph. And then the other thing that you need to keep in mind is horizontal asymptotes. Remember that at this level in pre-calc, we're not going to do slant asymptotes or what are called oblique asymptotes. We're only going to look at vertical asymptotes that are generated by denominator setting equal to 0 kind of things, and horizontal asymptotes. Every single graph that we do will have a horizontal asymptote and at least one vertical asymptote. Some will have more than one vertical asymptotes. Some graphs that we do will have a hole. Some graphs that we do will not have a hole, but no slant asymptotes. We're going to graph each of these using either a light line or a dotted line as your to represent your asymptotes. You need to show the asymptotes, and you also need to indicate any holes with a small open circle. And if you don't draw the hole, yes, on a test I would take off credit for that. I'm going to also ask you to the left of each problem to answer some questions about the algebraic answers to wholes and asymptotes and intercepts and that, and you shouldn't have any decimals there. So really you should be able to compute all of those things on the left algebraically and then represent them on the graph. And of course you would have Desmos to do all of this to work along with you. So what I think I'm going to do is splice in Desmos segments for each of these 4 graphs. There's going to be 4 graphs here. For each of these 4 graphs, I'm going to splice in Desmos segments at the beginning so that you can see how the graph looks and kind of explore the graph a little bit with Desmos, and then we'll write stuff down and actually draw the graph on the paper. Couple of side notes. First of all, if you happen to have a hard copy of this packet, if it's year 2020 right now that you're listening to this, I managed to get about 2 of my classes hard copies of this packet, and I was not able to get hard copies to anyone else. I would say you don't really need to print all of this. If you want to just do this on notebook paper, you should be able to do that. But the last question that we're going to do in a few minutes, number 14, I've changed. So photocopied, it has a different equation than what you see in front of you. And it's because I wanted to do something a little bit different with the graph, and I didn't like how the given equation laid itself out on the graph space. So anyway, as we get to number 14, I'll remind you of that and show you the change. But just keep in mind that if it's year 2020 and you have a hard copy that you got from me of this packet, then just put a little note next to 14 that it's going to look different, and it's because I've changed it since I photocopied it. So moving along, I'm going to have you pause the video here and switch over to Desmos, and then I will talk you through graphing it. Is the Desmos video for the lesson 3 notes example number 11. And I just kind of want to walk you through how to graph each of these examples. And I know you know the basics of typing in equations and looking at the graph of something, but I want to just make sure that everybody's on the same page, what's important, what's not important, and what are some little tips and tricks that you can use. Maybe not so much tricks, but just different ways that you can use Desmos to help you analyze the graph of a function. And these are going to be rational functions. So the first thing is that I'm going to start each of these equations with y1 equals, and you literally just type y and type the 1, and the Desmos will automatically make it a subscript. You don't have to do anything but type a y and a 1. And if you follow x or y immediately with a number, Desmos converts it to a subscript. So I'm going to type y1 equals, and then if you just hit the divide sign, which is the slash on the question mark key, the slash on the question mark key, it will automatically give you a fraction. And so the first example here, number 11, is 2x plus 1 over x minus 3. And I put my graph into projector mode. I think you saw me do that at the beginning of the video, just so that you can see it better. You don't need to do that, but I like to do that when I'm making videos for students. Also, I didn't click home because I had been doing some other graphing. So if you click home, actually your graph is going to end up looking more like this. I'm going to change the color to blue just because that's the color that I've used in the other part of the video. Which actually I made before I made these Desmos graphs, so I apologize if what I'm saying here and what I'm saying there don't exactly match up chronologically, because I made that video first, but I'm going to put this splice in before what I made first, if that makes any sense. Anyway, you can use your scroll, if you've got a mouse with a little scroll ball, or if you're using a MacBook or a computer that has a 2-finger scroll, you can scroll to zoom in and out, or you can pinch, or you can use these plus and minus to zoom in and out. And what I want to do is, first of all, show you that if you click on anything that Desmos shows you as a gray, if you click on the function, Desmos will give you these gray dots, and those dots mean that there's something special about that point. And if you click on those points, Desmos will give you the x and y values of those as ordered pairs. And so here, this would be my x-intercept, negative 0.5, which on the paper we're going to write negative 1/2, and we'll talk later about how to find that algebraically. And this one is negative, the y-intercept, which is negative 0.3 repeating, and that would be negative 1/3. And again, in a minute, I'll show you about finding that algebraically. Now, you don't have to do anything else in Desmos. In fact, you don't have to do this in Desmos at all, but I would strongly recommend you playing with these functions in Desmos just so that you can get an idea of what they look like before you actually put your graph on graph paper or on paper. So the first thing that I'm going to do is approximate what I think the asymptotes are, and graph those asymptotes just to make sure that my computation of the asymptotes is correct. So here it looks to me like there's an asymptote at x equals 3, a vertical asymptote, and that would make sense with the denominator here. So I'm going to type literally x equals 3. I'm going to make that a dotted line in red because I like my asymptotes to be red, and it looks like I had it in the right place. Then it looks like there's a horizontal asymptote at y equals 2. And remember that if the degree of the numerator and denominator are the same, then it's the ratio of the leading coefficients, 2/1. So here, y equals 2. I'm going to also change that to a dotted line that's red. And now I have my asymptote at y equals 2, my asymptote at x equals 3, and my function with an x-intercept and a y-intercept. Now, if you're wondering why I had you type y1 equals here, when you're drawing the graph of this function, you're going to want some points that go on the function. So the points that you would want to graph along there. So what I'm going to do is click in the last equation slot here. And then I'm going to go up in the top left corner to the plus sign where it says add item here. And when you click on that, it gives you a drop down menu, and you want the table choice. So I'm going to choose to add a table. Now the table comes up automatically with x2 and y2. I'm going to get rid of the subscript for the x. I'm going to change the subscript for the y to 1, and all you have to do is delete the 2 and type 1. You don't have to make it go low or anything. There's no special key stroke that you have to do for that. And the graph on the paper has from -6 to about +9. Just for my own use, I like to go a little bit farther. So I'll start at -7. So if you type -7, what it does is it takes that -7 value and it plugs it into whatever you said y1 is, and it computes y1 for that x value. If I then go down and type -6, now I've got two numbers in there, and if I haven't done anything in between, I can just hit return, and the Desmos assumes that I am using a pattern. And I'm going to go up to about 9. Well, clearly I went a little overboard there. I also want to change the color of my points to black. I don't know why, I just do. And so now I have the graph of my function in blue. I've got my vertical asymptote here in red. I've got my horizontal asymptote here in red. And then I also have different point values. And again, it's a lot, and you don't have to graph all of those points, but it gives you an idea of some of the points that you can graph to give you a good shape of the graph. And over here, when you're eventually drawing the graph, I would just pick every few points and pick the ones that are easy. I can draw 1.3, -4, 1 is an easy point to graph. 1, -1.5, 2, -5. Those points are also easy to graph. Make a special note of where the values are undefined. So for example, here at x equals 3, that y value is undefined because that's where you had the vertical asymptote. And when the y value is undefined, that actually means that this x value is not in the domain of the function. So the domain of this function would be negative infinity to 3, not including 3, and then 3 to positive infinity. And we're back now. And I made just a little screenshot of the graph of the function so that you can just kind of be reminded of what we did in the Desmos video. And the funny thing is that I haven't made the Desmos videos yet, but assuming that you've just watched me make this in the Desmos video, sorry, I'm just a little loopy this morning. So anyway, you can see this graph here, and we're going to make a approximation of the same graph then for ourselves. Remember that the denominator, where the denominator is equal to 0, those are the numbers that are left out of the domain. And so basically your thinking is that here x minus 3 cannot be equal to 0, so x cannot be equal to 3. And any values that you get that x cannot equal based on making a denominator 0 are either going to be a whole or a vertical asymptote. And the only time you have a whole is if something cancels. Since nothing here canceled, then it has to be a vertical asymptote. One or the other, can't be both, can't be neither. And so in this case, your vertical asymptote is x equals 3. And because nothing canceled, there's no holes. And your horizontal asymptote, remember here, we said that you have to look at the degree of the numerator and the degree of the denominator, and they're both first degree polynomials. And when they're both the same, you want to look at the leading coefficient of the numerator and the leading coefficient of the denominator, and you want to look at the ratio that those two numbers make. And so 2 over 1 is just 2, and so your horizontal asymptote is 2. Your x-intercepts you compute by setting the numerator equal to 0. And so here I'm going to say, okay, 2x plus 1 equals 0. So 2x equals negative 1 and x equals negative 1/2. And so your x-intercept is x equals negative 1/2. And hopefully we talked about that when we made the video. And your y-intercept, remember that the thinking here for the y-intercept is that if you have this function algebraically, you kind of, I dropped my pen, that's crazy. You kind of just ignore any of the terms that have x's in them, and then what's left, just the constant terms. That fraction, or if it's not a fraction, it might be a whole number, would be then what is your y-intercept. So y here equals negative 1/3. And remember that Desmos will give you the decimal values, and I need you to give me the values not as decimals. When you draw this, remember that, first of all, I want you to show the asymptotes either as a lightly drawn line or a dotted line. I'm going to draw them in red every time. So whenever you see me drawing asymptotes, they're in red. The vertical asymptote is at x equals 3. It's a little hard to do on my iPad, so bear with me, please. So there's my, and please use a straight edge, like I clearly didn't. I don't know if I can live with that. Hang on a second. You might not even see that part of the video. I don't know what. I'm crazily redrawing the not straight part of the asymptote. Okay, and then let's go to the horizontal asymptote, which is going to be at y equals 2. And so that's going to be about here. Again, please use a straight edge. And then remember that you can pull points off of Desmos by making a table, and I didn't show that in the screenshot off to the side. But let's see here. I don't need to graph every single point that was in the table, but just a few points to kind of give me some approximation. For example, I know that at when x is -4, the value of the graph is +1. So I'll put that point right about here. And then how about at -2, the graph is 0.6. So that's really about here. And then I do want you to graph the x-intercept, which is -0.5, and the y-intercept, which is -1/3. And you can kind of get a feel for the curve of the graph there, but you also want to continue to graph some points as you're getting closer to the asymptotes. And so as I go to +1, it's -1.5, and at +2, it's -5 already. And you can kind of get a feel for how the graph then behaves close to the asymptotes. So like this here. And then on the other side of that asymptote, so let's start at x equals 4, we've got a point up here at 9. X equals 5 is 5.5. So about there. And then I can kind of skip down to farther out. Now this graph is 5, 6, 7, 8, 9. At x equals 10, it was 3. So I can kind of, again, approximate that 10,3 would be about there, maybe a little bit farther out. But that's a good rough idea of where those points would be. And there's a good rough sketch of that graph. Can you hear those birds in the background? I don't know if you can hear that. It's springtime when I'm making this video in my house, and the birds are just all kind of migrating. Anyway, let's move on to the video for the next equation. Go ahead and write that down if you need to. Type it into Desmos, and I'll switch over to my Desmos video. For example 12. So remember that we want to type in the equation using y1 equals, so that we can make the table of values later. Then I'm going to hit the divide sign so that I can create a fraction for myself. And if you have already factored the numerator and denominator, don't type in the factored versions, and especially don't type in the simplified version, because you need to see that there's a hole in the graph, and you can't accurately represent the hole in the graph if you've already simplified and canceled out parts of the equation. So anyway, I have y1 equals x squared minus 2x minus 3 over x squared plus 6x plus 5. I'm going to change the color of the graph itself to blue. And I see here that it looks like I have an asymptote, a vertical asymptote at x equals 5. So let me just check that. X equals 5. Oops, -5. that didn't even make sense, did it? You were like, what is she talking about? I'm going to make it a dotted red line, and it looks like I've got that asymptote fairly well nailed down. And then it looks like I have a horizontal asymptote maybe at y equals 1. So let's try y equals 1 for the horizontal asymptote, and hint, I've done these problems ahead of time, so I'm not actually guessing. But there's an asymptote at x equals -5 and another one at y equals 1. But because I have a second degree equation, I feel like there should be another x value that is restricted from the domain. And so I'm wondering if I have a hole somewhere, and hint, there is a hole. And so just kind of superficially, I can slowly drag the cursor over like I'm holding down the cursor as I go over the graph, and I happen to know that the hole is at -1, and I'll try to hold it here for a minute without flinching, but if you are careful, you can show that the hole is, or that there's an undefined point there at -1 where the y value is undefined, and that would be where your hole is going to be. But it doesn't help you compute the y value. So you actually have to compute that y value algebraically. There is absolutely no way to pull that off of the graph other than just by looking and guessing at it, and don't try to guess. So we'll talk in a minute about computing that algebraically, but anyway, you see that there's that hole there, or that missing point at x equals -1, and the vertical asymptote at x equals -5. I'm also going to create a table. So again, I'm going to go up to add item, add a table, change x2 to no subscript, and y2 to y1. And then I'm going to, now I see the graph space that Miss Applebacher gave you starts at -12. So let me start with -13, -12, and then I'll just put in a bunch of x values until I get a little bit beyond the space that I have to graph. And I'm going to change the color of those points to black. And so here I just also to underscore the fact that this x is -1 here would be that that hole, and in the table it shows it as an undefined value both on the graph and on the table. -1 is undefined and -5 is undefined. So I have approximated my asymptote and my hole correctly, and we'll talk about how to do those things algebraically in a minute. Little piece of video here because I realized that I didn't, one of the things that I didn't address in number 12, and I want to make sure I do before you actually try to put it on the paper, is that there is a hole, and in a minute we'll talk about algebraically how to compute that hole. And please keep in mind that the hole has to be computed algebraically. You can't compute a hole, the y value of a hole, by looking at the graph or looking at a table or anything, because it will always give you that it's undefined. You're actually looking for the algebraic value of something that doesn't exist. So you're saying this is missing, and so you can't compute it. So we said that there's a vertical asymptote at -5. But when we looked at the values in the table here, we can see that there's another place that's undefined at -1. And I think I talked about the fact that you can arrow over that and see that it's undefined over here, and that it looks like a little hole. You can actually graph that by graphing the ordered pair. Now I'm going to tell you it's -1, -1, and we'll talk in a minute about how I got the y value. But if you just type parentheses -1, comma, -1, that'll give you a point there, but I don't want the point to be a point. I want it to be an open point. So I'm going to hold down on this. I'm going to change that to open point, and that automatically then makes the hole look like a hole, like what you're expecting it to look like. And I can even make it label that hole. so that when I switch over in a minute to the video on the PDF, I'm going to show you a graph that has that hole labeled on it. I'm going to, just for a minute, turn off all those extra points, and just so that you can kind of see the graph here like that. And now you can see the graph itself. You can see the whole graph and the asymptotes. So here's the graph that I'm hoping we just made together in Desmos. Without the table of values, hopefully you have that in front of you. Remember that you don't have to graph the whole. I just kind of wanted you to get an idea of what it looks like. But the asymptotes are there, and I've put the whole on the graph, and you can kind of get a feel for what this graph looks like. Now, I am going to come back over here. Here's what we want to do algebraically. And you might be needing to kind of, and hopefully I said this when I was making the graph, you kind of need to be thinking about both the algebra and the graph more in parallel than I'm able to show on the video, because you almost need to factor it and decide about the denominator and the x values that are restricted from the domain before you actually are able to put any asymptotes or holes on the Desmos graph. But anyway, let's walk through the algebra of all of this and what I need for you to do. And again, I'm not going to walk you through how to factor, but I want you to factor the numerator, factor the denominator, and then cancel anything that can be canceled. So go ahead and pause the video here and factor. And when you factored, you should have gotten in the numerator x minus 3 times x plus 1. And in the denominator, you should have gotten x plus 5 times x plus 1. And then you're going to cancel the x plus 1s. And so simplified, this expression is x minus 3 over x plus 5. Now, really what we're saying here is that x cannot equal negative 5 and x cannot equal negative 1. And each of these things is either a whole or a vertical asymptote. And because the x plus 1 is the factor that canceled, this is going to be the x value of a whole, and this is going to be the vertical asymptote. So your vertical asymptote is x equals negative 5. And then the whole, remember that you need to go back to the simplified expression. We said that the whole is where x is negative 1, but then you need to find the y value. So negative 1 minus 3 over negative 1, knew that was going to happen, plus 5. Negative 1 minus 3 is negative 4. And negative 1 plus 5 is positive 4, so that whole thing equals negative 1. So your x value of the whole and your y value of the whole give you the ordered pair negative 1, negative 1. To compute the horizontal asymptote, you want to again look at the degree of the numerator and the degree of the denominator, and they're the same. And the leading coefficient in the numerator is 1. The leading coefficient in the denominator is 1. And so your horizontal asymptote is 1 over 1, which is just y equals 1. Now, for your x-intercepts, remember that you set the numerator equal to 0, or you look at what makes the numerator equal to 0. But here's the interesting thing that you need to kind of make note of. It's the numerator after you've canceled. So here, x equals 3 is an x-intercept. Because this, x equals -1, is not part of the graph. It's not on the graph, or it's not on the domain of the graph, because it's a hole. And so if it's a hole, it can't be an x-intercept. So x equals 3 is the only x-intercept, and you see that in the graph. So x equals 3 is the x-intercept. And then remember that for the y-intercept, we're just going to look at the constant terms. So -3 over +5. Ignore the rest of, I'm not going to obliterate it with black this time because I want you looking at the equation. So your y-intercept is y equals -3/5. So before we start drawing the actual graph, I want you to just kind of take a look at the graph from Desmos, take a look at the algebra we just did, make sure you track with all of that. And then let's put the asymptotes on the graph first. Wait a minute to change colors. And so let's do the x equals -5 asymptote. And again, it's a little tricky on my iPad, so I'm sorry for those of you seeing this on a video. Oh, that wasn't so bad. Okay, so there's my vertical asymptote. And now my horizontal asymptote is y equals +1. This is also going to be a little bit tricky. I think I'm nailing it until I drop my pen. Okay. So there's my horizontal asymptote. So I've got my 2 asymptotes drawn, but I also want to draw my hole, which is going to be an open circle at -1, -1. And so as I draw my graph, I'm going to act like that's a point on the graph as far as kind of where I draw the line of the function, and then just skip over that point. And then I'm going to go back to the table that I drew in, or that I computed in Desmos. At -10, the graph is 2.5. That's right inside of where I put that writing. It's right there. I think, hang on a second, I actually want to move, hang on. There we go, I needed to move that because I really want to draw this a little bit more accurately than I was on track to do. So anyway, here's where that -10, 2.6 is, -9, 3 is about here, so not a lot higher. That's probably too high, in fact. Let me move that down. And then -7, 5 is up here, and -6, 9 is already, and that's also going to bump into what I've written, so let's not do that. But it kind of goes then like this. That's that side of the graph. And then on the other side of the asymptote, at -4, it's -7. And at -3, it's -3. And I've got my hole at -1, -1. I'm going to kind of treat that as a point. I'm just going to graph around it. And then at I also need to do my x-intercepts and y-intercepts. So my y-intercept is about -3/5, so right about there. And then let's say 3, 0 is my x-intercept. And there's not a lot of other good points because everything there gets really close to the asymptote. I kind of want to make this just a little bit heavier, and I want to make this point a little bit bigger. So then this side of the graph is going to look something like this. two more problems, and first of all, I want you to just take a minute and either write down or start typing into Desmos number 13 so that we can go ahead and look at how to actually go ahead and analyze this graph using Desmos. Remember that we want to start with y1 equals, and we have to type the equation the way it is before you factor or cancel or anything, because that will change what the graph looks like or how the table behaves. And so I will type a divide sign to give myself the fraction, and then x squared minus 5x plus 6 plus 6, and then I have x squared in the denominator plus x minus 2. I like to change my graphs to blue, don't ask me why. And that's kind of a funky looking graph, and we're going to talk about some of the things that you see here. But the first thing that I want you to notice is, can you tell that there would be two vertical asymptotes, one here-ish and one here-ish? And so this one over here, if I zoom a little bit closer, well, that might not be helpful either. If I zoom maybe to here, it looks to me like that asymptote is going to be at about x equals -2. And I like to make them a dotted red line. That looks about right. Yeah. And the other one looks like it's probably at x equals 1 here. So let's try x equals 1, dotted red line. Now the horizontal asymptote here is tricky, and so I kind of want you to see, first of all, that it looks like you have something down here because of this little doop-de-doo. But what I want you to remember is that horizontal asymptotes have nothing to do with the middle of the graph. They're only about the end behavior as you go to infinity. And so actually it might help me to go back to home and keep my x values, so my x-axis, keep my y values the same here, but to actually change the x values to really big numbers so that I can see. I might even change my y values to like -5 to +5. And so here, it looks to me like that that horizontal asymptote here would be at y equals 1, because this is y equals 2. Can you see the numbers there? And so I would say that my horizontal asymptote is at y equals 1. Yeah, and that looks about right. I'm going to change that to a dotted red line. And then I'm going to go back to what I had as far as scale goes. It's okay that the graph crosses the asymptote here, and in the next graph we'll have the same scenario. So those are the asymptotes. There's no holes here. It's a second degree equation, and we've got two x values that are restricted from the domain, so there won't be any more. But I do want to talk about what's happening right here on the graph. And if you just keep your graph set where it was, or if you're zoomed out just a little bit, it kind of looks like a bounce, like the graph comes down, touches the x-axis, and bounces off of it and comes back up. But if you zoom in really close, you'll see that you have two x-intercepts, and they're distinct x-intercepts, and the graph actually briefly goes below the x-axis, just slightly below. And there's an x-intercept at x equals 2 and another x-intercept at x equals 3. And what this other, remember that Desmos gives you gray dots for places where Desmos is telling you this is a special point on the graph. And what's actually happening is if the graph goes down, it's positive here, it's negative here, and it's positive over here, and you know you have a 0 there. At some point or at some place, the graph has to change direction. And so what Desmos is saying is that this is the lowest y value in this neighborhood of the graph. Remember that we talked about local min and local max. That there's in this one particular section of the graph, in this neighborhood of the graph, this point right here is the lowest y value of all the surrounding points, that all these other points are higher than those y values, are bigger numbers than negative 0.039. Now we're talking about really super small decimal numbers, but mathematically that has to happen. It comes down and comes back up again. There has to be a place where it changes direction, and so that's this point. You do not have to graph this point, but I do expect you to try to make your graph reflect slightly the fact that there's an x value here, an x value here, and it goes slightly below the x-axis there. Oops. I also forgot to show you making the table for this one, and I wanted to do that real quick because I want to be able to then talk about it in the video. So this is actually a second spliced Desmos section. I don't know how I'm going to put that into iMovie, but I'll figure it out, and it won't be a problem any longer by the time you're seeing this. So anyway, I had to redraw the graph. I had already deleted all my equations and everything, but that's just silly and it doesn't really matter. So I'm going to add item up here, this plus sign, and I'm going to add a table. I'm changing the x2 to just x, and I'm changing the y2 to y1. And I see that Miss Applebacher only went from -5 to +5 on the x-axis on the handout, and so I'm going to go, let's say, from -6 to +6. So I'm just going to start typing the first two numbers, and then the rest of the numbers I just press enter over and over again, and Desmos will fill in, assuming that I want to go in the same pattern. So these are the values that will generate points, and just remember, you don't have to graph all of these, but you just want to graph the ones that are easiest to graph and to give you an idea of the shape of the graph. The couple of things I want you to notice, we talked about the two x-intercepts here, but that the graph dips slightly below between x equals 2 and x equals 3 here and here. The other thing that you want to notice is there's an asymptote at x equals 1 and a y-intercept at x equals 2, but that the graph really is very steep between coming near the asymptote at positive infinity to, and that's where it hits the asymptote, and to where there's this x-intercept here at x equals 2. And even here, the steepness between x equals 1 not having a value, so it's at infinity, to this is just 1 1/3, so in a third of a space on the graph, the graph dropped all the way to y equals 1. So here I used two of the screenshots from Desmos, starting with the overall graph. And this is what we came up with some asymptotes. Let's back that up with the algebra. Remember that you need to factor the numerator and denominator first. So if you haven't already done that, take a minute, factor the numerator, factor the denominator, and then put the video back on. And so you should have gotten here x minus 2 times x minus 3. Remember that the factoring when it ends in 6 and has a 5 or a 1 in it is going to be tricky. The denominator, you should have gotten x minus 1 and x plus 2. Nothing cancels, so there are no wholes. And so remember that that automatically means that both of the values that are excluded from the denominator, x equals, or x cannot equal 1 and x cannot equal negative 2, those values are both going to be vertical asymptotes. And so here you're going to have two vertical asymptotes, x equals negative 2 and positive 1. There's no wholes. Your horizontal asymptote, again, is going to be 1 because the degree is the same for both the numerator and denominator, and your leading coefficients are 1 in the numerator and denominator, and 1 over 1 is y equals 1. Now remember that your x-intercept is, x-intercepts in this case, plural, is going to be where the numerator equals 0. So the numerator equals 0 at x equals 2 and x equals 3. And so you're going to have two x-intercepts. And what I wanted to do then over here is kind of show you what that's going to look like. It's hard to see unless you zoom in on the graph really closely. And so take a minute and in Desmos, just take a look, because if you use your full screen Desmos, it looks like there's just one x-intercept and that it kind of touches and then bounces off, like almost like a double root in a polynomial function would look, but you have to zoom in closer, and as you zoom in closer you can see that you've got two x-intercepts. And just in case I didn't mention this when I was making the Desmos video, the fact that Desmos puts a point there and you're like, what is that point doing there? That's actually going to be a local minimum. And if you were to click on that, Desmos would give you the x and y values of that point. That's not something that you are going to need to be able to do this year, but next year when you take calculus, you're going to want to, you're going to need to look for turning points even in awkward graphs like this, and there are going to be other ways to algebraically compute those values. You can always use Desmos to verify. And also, if you're doing an AP course, I think that the APs require you to use only graphing calculator and not Desmos, and your graphing calculator would also compute that minimum. And if you have any questions about how to do that, you can get in touch with me, and I can show you how to do that. But it's really not required this year. So anyway, if you're not sure here off of this graph that both 2 and 3 are x-intercepts, separately just zoom in. So over here, your y-intercept, remember that for your y-intercept, you're just looking at the constant terms. And so I'm just looking at positive 6 over negative 2. But remember that if I do positive 6 over negative 2, I have to reduce that fraction. So 6 divided by negative 2 is going to be negative 3. And so my y-intercept is negative 3. So let me just real quick put my x and y-intercepts on the graph just so I don't forget. I think I've forgotten the last one. And then my asymptotes, so my vertical asymptotes are at negative 2 and positive 1. So negative 2 and positive 1. And then I have a horizontal asymptote at y equals 1. So y equals 1. There we go. And so for this graph, actually drawing the points is going to be just a little bit tricky. So I'm really going to use that table that I had created in Desmos, and I'm going to start, let's say, the the stuff to the left, and the graph to the left of the asymptote at x equals -2 is kind of up high, and I didn't give you a really good space for that. So let's just start where -5 is just a little bit higher than x equals +3, +3.1. So I'm just going to kind of put that point right about here, and then -4 would be 4.2. That's getting up pretty high pretty quick, and -3 is 7.5. That's already off the paper. So really your graph is going to look kind of like this. And then in the middle, I am going to look from -1 is -6. That's already off of the space I gave you. And at 0, we already graphed the -3. And so I kind of want to look at my Desmos graph, because that's not enough to help me get the shape of it. And I see that the graph goes up to the y-intercept and then goes just a teeny bit higher before it goes down again. And I kind of want to reflect that shape when I'm drawing it. So I'm going to kind of shoot to have a kind of a little local maximum there. And so the graph goes up and then a little bit higher, and then it goes back down toward the asymptote like that. And then on the other side, here's where I don't want you to get confused about the difference between horizontal and vertical asymptotes, because a vertical asymptote cannot be crossed. You can't draw your graph across a vertical asymptote. That is an x value that does not exist in the domain of the graph. But a horizontal asymptote can and often is crossed. The horizontal asymptote is only about end behavior and not about how the graph behaves in the middle. So in this graph, if you only look at the table, it looks like there's no points between 1 and 2. But if you look at the graph actually comes down from near the asymptote up here, goes through, and I didn't do a good job of that. I'm going to redraw this, and you might not even ever see that. So the graph comes down near the asymptote there, barely goes through the x-axis like that, and then as you get out to 4, it starts to come up slowly toward the asymptote like that. So there's number 13. Take a look at that. Make sure that you are okay with each piece of that graph. I think the video here is going to be a little bit disjoint because I forgot to add a section to remind you that I've changed number 14. So if you could please take a look at the paper you have in front of you, look specifically at number 14. If I gave this to you, physically gave you a copy of a packet in my classroom in March of 2020, you're probably in my 5th or my 7th period class in the spring of 2020, you got a photocopied packet that has a different equation for number 14. I've changed it between handing you the packet and making the video. I decided to use a better equation. So if you could change that equation to what you see in front of you. If you're printing this off of Google Classroom in 2020, or if you're looking at it in a future year, then don't worry, I hopefully will have updated the packet by that point. So take a minute and copy down the new equation for number 14. So before we listen to the clock, and then we listen to the birds, and now they're working on the lawn outside of my house and kind of doing loud mechanical work on the landscaping in my development, so you may hear people working on lawns and stuff. My apologies for all the background noise. Usually making videos at home is quieter than making videos at the school. Anyway, take a minute, write this down, start to type it into Desmos, and then I'll switch over to the video. Last but not least, this is example 14. And I see that I want to start with y1 equals, so I need to click in there to get it to work when I type. Y1 equals, and then type the divide sign to give myself the fraction, and then 3x, I don't know why I did that. Type the divide sign to give myself the fraction, 3x to the third power. Glad this is the last one, because it seems to be going downhill. So you know how I had to split up the video in my last you don't need to know any of this, but in my last video I had to break up the video because I forgot to put the table in. It's because my friend was texting me pictures of her cute dogs, and I just completely got distracted. But the dogs were pretty cute. Anyway, you don't care about any of that. So the denominator x to the third power minus 3x squared minus 10x. All right, I'm going to zoom out just a little bit. This is another oddly shaped graph, but it looks to me like there's two vertical asymptotes. But wait, if the denominator is third degree, there might actually be a third x value that's missing, because if you solve this polynomial, if you just look at the denominator, it's a third degree polynomial. There should be 3 places where that is equal to 0, or 3 solutions to that. And so if you are, hang on a second. Oh, that's a flower shop in New York. I don't know why I wanted to see that. It just made me interested. So if you're thinking about the degree of the denominator, often, not always, but often is equal to the number of restrictions on the domain, I see 2 places where there are vertical asymptotes, but there would be a third one, so I'm wondering if there's a hole somewhere. So just kind of keep in the back of your mind that there may be a hole. Looks to me like this one, and I'm going to zoom in just a little bit here. There might be one at x equals -2. Let's try x equals -2. That looks about right. And then the other one's a little bit more tricky because this is not as steep a slope, but I think maybe 5. Does 5 sound about right? So let's try one at about x equals 5. Yeah, that looks about right. And the horizontal asymptote, again, is tricky because it looks here like, and I told you earlier that there was going to be a place where the graph crosses the horizontal asymptote. So let's say that the horizontal asymptote here is 3. And keep in mind that the degree of the numerator and the degree of the denominator are the same. And so it's the ratio of the leading coefficients, +3 over +1. So that would make sense that y equals 3 is a horizontal asymptote, dotted red line. And I actually want to zoom out quite a bit more as I'm looking at this, and we'll talk a little bit more about that spot right there in a minute. Let's make our table so I don't forget this time. Add a table, change x sub 2 to just x, change y sub 2 to y sub 1. On the graph space that I've given you, I've gone from -10 to +13. So I'm going to start at -11. I didn't turn off my sound. Sorry, they're emailing me from the school. -11, -10. And remember, once you've typed the first 2 x values in a pattern, then Desmos will continue that pattern. If you haven't typed anything else or clicked anywhere else, just keep hitting enter, 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 and it'll just do all that without you typing. And it gives you a bunch of places where you can plot points. So we said that there was a vertical asymptote at x equals -2 and x equals 5. Another one, sorry, I keep forgetting to turn off all of my sounds. That's one of you wonderful people texting me. Hi. Anyway, so it's telling me that x equals 0 is undefined, and it looks to me like the function goes through there, so it's probably going to be a hole. And if I wanted to, I can click here and very carefully try to pause on top of x equals 0, and sure enough, that's a hole. What I forgot to show you in the previous video, I think I forgot to show you this, is that you can graph, you can show the graph of a hole. You don't have to, and it doesn't make sense to do it, but you can type, you literally type parentheses 0, comma 0. You know that you have to compute this algebraically. There's no possible way to find the x and y values of the hole, especially the y value, just by looking at the graph. So you have to do some algebraic computation. But Desmos lets you, I'm going to do this in blue, but Desmos lets you graph a point and then put a hole in the point. So you can, if you want to, graph that point, and then you can even have it automatically label the point. So I've got this labeled point here. I'm going to move this up. I think I'm going to move this up above the table. I don't think I can. Anyway, it doesn't matter. So that now I have that hole shown there at 0, 0. That's merely for show, and you don't need to graph that on Desmos. If you know where the hole is, you can just draw it on the graph on your paper. And so the graph that we just made should look something like this. And hopefully I talked you through all of that, and you also have a table with values that we can look at when we're graphing. And remember that you don't have to show the hole, but I just wanted to use it as a point to talk about. So coming back to the equation here, you can see, I hope, that you can't factor the numerator any farther, but that it's technically already a factored thing, 3 times x times x times x. The 3 and the x and the x and the x, all 4 of those things are factors of the numerator, and any of them can be canceled with something in the denominator, which is what's going to end up happening in this problem. I do want you to factor the denominator, and remember that the first thing you're going to need to do is factor out an x, which is a GCF. So go ahead and do that. And what you should get here is your 3x cubed over, and then you factored out your x, and then you get x plus 2 times x minus 5. Now I'm going to write this just a little bit differently than you probably have written it, and I'm going to probably end up in my own space of the graph. In fact, I know I am. I'm going to erase a little bit over here and change that graph so that it's like this. And I'm going to rewrite the numerator so that it's 3x squared times x. And I just kind of want you to look at the original equation and make sure that you see that I've not changed anything but how it looks. That 3 times x squared times x is the same as 3 times x cubed. Because really what I want to do is show you that those x's cancel, and so x equals 0 is going to be a hole. But because these other two don't cancel, x is negative 2 and x is positive 5, those are both going to be vertical asymptotes. And that my completely simplified form of the equation will be 3x squared over x plus 2 times x minus 5. So make sure that you track with my algebra there. And then we said that the vertical asymptotes were x equals -2 and x equals +5. We said that the x value of the whole is 0, but we need to compute the y value of the whole. And so I'm going to come back over here, and if I substitute, I take the simplified version of the equation, substitute in zeros for the x's, but it doesn't matter what the denominator is, because the denominator is not 0. We already got rid of that number that canceled, and that would have made the denominator 0. But what you see in the numerator is, hang on a second, what you see in the numerator is that 3 times 0 is just 0. And so the value of this whole thing is equal to 0. So that's the y value of the whole. And so your whole is the point 0, 0. So your whole is the point 0, 0. Your horizontal asymptote, let's come back to here and remind you that the degree of the numerator and denominator is the same. The leading coefficient in the numerator is 3. The leading coefficient in the denominator is 1. And so my horizontal asymptote y equals 3 over 1 is just y equals 3. Now I want you to slow down for a second, specifically look at the simplified version of the equation. To find an x-intercept, remember that your thinking is set the numerator equal to 0. But if you do 3x squared equals 0, you end up with x equals 0, and that's a whole. So instead of having an x-intercept at x equals 0, there's a whole at x equals 0. So when you look at the graph, it looks like there's a value of the function at 0, 0, but in actuality, it's a whole. So in fact, there are no x-intercepts. None. And kind of look down here. If I hadn't graphed this point, which I did intentionally, if all you were looking at was the original graph of that original function, it would look like, if you zoomed in, the graph goes through 0, 0. Because remember, Desmos doesn't automatically show you a whole. But then when you do the algebra, you can see that there's a hole there, and that's the only place where there would be an x-intercept, and it can't be an x-intercept if it's a hole. The other thing I want you to see is that that's the only place that the graph, remember it's a function, so it has to pass the vertical line test, but that's the only place that the graph looks like it comes near the y-axis, so there's also no y-intercept. So no y-intercept. So take a look at the algebra, make sure that all of that makes sense to you before we start graphing. I'll start with my vertical asymptotes. I've got one at -2, and I've got another at +5. And then my horizontal asymptote is at y equals 3. Okay. So those are my asymptotes. I'm also going to already draw my hole here so I don't forget. And I have to make sure, because it's on the axis, make sure that it's fairly clear that you have a hole there, so that when the teacher is grading your paper, they know that you know. Because that's really what testing is and quizzing is about, right? To make sure that the teacher knows what you know. So then I'm going to start by graphing. And this is another, by the way, interrupting myself, this is another example of a function where there is a horizontal asymptote, but that the graph crosses the horizontal asymptote, and that's going to happen over here in this section to the left of x equals -2. So if I look at my points to the left of x equals -2, at -10 it's 2.5, and that's about here. And let's skip over to, let's say, -5 is also about 2.5. Well, that's kind of crazy. So at some point between -10 and -5, the graph kind of dips down a little bit. And 2, 4, 5. So I don't know if you can kind of imagine what I'm talking about here, but if this is -5, 2.5, and this is -10, 2.5, the graph is really slightly going down through there. And so you can't really reflect that in your drawing, because this is one of those cases where your pencil is too thick to actually accurately draw the graph. When you zoom in on Desmos a lot, you'll see it. But what happens then between -5 and the asymptote at -2 is interesting, because then it goes up really fast. So at -4, it's just slightly higher, but then at -3, it's 3.75. That's where it crosses the asymptote, and then it goes up. So your graph actually does, over here, does this kind of thing. But over here, it just kind of dips down slightly and then comes back up. I didn't do a good job of drawing that smoothly. I think I'm going to draw that whole thing again. I know you guys think I'm crazy. I'll draw that whole thing again. So it goes up really fast through here, and it barely dips down between 10 and -5. It's hard to see. So that's not really a straight line, and again, I still didn't draw it very accurately, but it's hard to get that accuracy there. It's not a straight line, but it's awfully darn close. Then the middle of the graph, then the section between the two asymptotes, at -1, we've got -0.5. And at +1, it's -1/4. And then at +2, it's -1. And at +3, it's -2.7. And at 4, it's -8 already, and I don't even have enough space here to draw that. So the graph will kind of do this. There's a hole there, and then come back down like that. And then to the right of that asymptote, starting with x equals 6. Oh, I did something funky on my computer. At x equals 6, it's 13.5, and I don't even have a graph high enough for that. It really starts to get within reach when I get to x equals 7. So x equals 7 is about 8.1, and so that would be maybe about here. And then x equals 8 is 6.4, so maybe about here. And then x equals 10 is 5. So that this part of the graph kind of goes like that.